analysis of urban millimeter wave microcellular networks in VTC 2016 fall. So in the Manhattan-type urban vehicular networks, we have very dense skyscrapers where severe signal blockage and attenuation will make the signal very weak. And also there are hundreds of clustered users at the intersections, which generate very heavy load for the base stations. The diverse sets of the terminals, like the vehicles, the pedestrians, the cyclists, and others, have different types and various kinds of applications, like the vehicle safety and infotainment. So this makes the Manhattan-type urban vehicular networks the most challenging environment for millimeter wave communication. So there are several stochastic geometry based analysis approach to model the networks of the urban millimeter wave networks. So there are some works of the analysis of the millimeter wave communication considering blockage. So the idea is to model the location of the buildings as a Poisson point process on a two-dimensional plane. And in this case, the buildings are modeled the buildings are modeled as randomly oriented, and if the link is blocked by a building, it is treated as a non-line of sight base station. Where it's not blocked, it's a line of sight. And these different type of the links are differentiated by different pathloss exponents. And there are several other work of the Manhattan type network analysis without considering the millimeter wave communication. So basically, they have the same idea as the previous work, considering the in the millimeter wave with blockage. The only difference is that in this case, the buildings are just seen as the regular rectangles, and the streets are very perpendicularly located on these urban networks. And there are also some analysis with stochastic geometry of vehicle-to-vehicle communication without millimeter wave. So in this paper, we are going to build up analysis framework of some realistic urban microcellular pathloss model, and we are going to provide a very tractable analysis of the vehicle-to-infrastructure communication based on this. So the main contributions in this paper is, first, we exploit a new urban pathloss model for millimeter wave microcells verified from the ray tracing results. And the second is that a new analysis framework for the outdoor millimeter wave using the Manhattan Poisson line process is proposed. And last, we, based on the results that we derived from the coverage probability, we quantize and compare the interference coming from the different locations of the streets. So for the system model, as we said before, so this paper uses a different pathloss model, which is based on Manhattan distance, which is different from the previous Euclidean distance-based pathloss model. So briefly, we show that from the prior work, we see that the Euclidean distance is not the right way to characterize pathloss. When the specifically, so the different pathloss exponents on different streets, even with different orientations, should be different. So in this second figure, we can see that this is an explanation of our pathloss model with Manhattan distance. So in this case, when we have a receiver located on one street and the base station located on a perpendicular street, and the direct link between them is blocked by an urban building. And in this case, the penetration effect through the building is very weak in the millimeter wave. So that's why we're thinking of the signal is not penetrates through the building. Instead, it travels along the street, and then it couples into the new direction, and which introduces a corner loss at the corner. So Euclidean distance is not the right way to characterize path loss, and we are adopting the Manhattan distance as the main metric to evaluate our path loss in this case. So to be specific, the path loss model is calculated by adding up the path loss on each individual segment of the propagation path. For example, the first part here is the path loss on the line of sight segment, which is the first segment of the whole propagation path, so like this red link. And this is a summation of the path loss on all of the non-line of sight segments of the path loss. And this is also added by some extra coulomb losses whenever it is coupled into a new direction of the street. So for the network model, we are considering the Manhattan-Poisson line process to model the urban streets, and also we are using Poisson point process to model the base stations. So for example, this is an example of the network model adopted in this paper. So there is a one-dimensional Poisson point process, which is denoted by this and this. So each of them will stretch into two different directions, and this formulates the grids of the street. And the vertical and the horizontal streets intensity denoted by lambda s, and the street width here is not considered in this paper. And the base stations randomly dropped on streets at Poisson point process. And in this paper, we are mainly considering analyzing the performance of the typical user on the horizontal street, the typical user which is located in the center of a horizontal street in the whole network, and the base station's intensity on the vertical and horizontal streets are lambda t. So for the coverage analysis, we use a new approach to find a very accurate and also very simple expression of the coverage probability. So the first thing is we consider a typical receiver O, and we formulate the signal to noise plus interference ratio in here. And it is formulated as the transmit power times the small scale fading, where U is the associated link path gain. And for the base station association rule, we assume that the vehicle is associated with the base station that is strongest. That means that with the smallest path loss. And for the interference and the noise, the interference mainly comprises of three parts. So they are from the interference of the line of sight street, which is the same street that the receiver is lying on, and the interference from the non-line of sight base stations on the vertical, which is the cross streets, and also the interference of the non-line of sight base stations on the horizontal streets, which are parallel to the line of sight street. And for the coverage analysis, we're following three steps of the analysis. So the first, we are going to first formulate the cumulative density function of the associated link path gain. And then we are going to calculate the coverage probability conditioned on the unknowing the associated link path gain. And finally, we are averaging over the coverage probability deconditioned on U, and finally get the final coverage probability expression. So for the result, we see that the CDF of the associated link path gain just a simple product of two exponential, which have very concise forms. And then conditioned on the coverage probability, which is conditioned on the associated link path gain, we are also able to show that it's in a very simple form, just the product of three very simple exponentials. After conditioning the coverage probability, the results is just a very simple integral, which requires very few calculations in computers. So based on the very simple results that we get from the previous analysis framework, we are going to quantize the different effects of the interference from different parts of the street. And specifically, we use Jensen's inequality to quantify this difference, to quantify the difference on the Laplace transform of different part of the interference. And for the non-line of sight interference and the non-line of sight, we respectively calculate the Jensen's inequality lower bound of the Laplace transform of the line of sight interference, the non-line of sight vertical street interference, and also the non-line of sight horizontal street interference. And for the non-line of sight horizontal street interference, we show that this is just can be expressed by a modified Bessel function of the first order. And we're also going to show that because of the parameters inside the arguments of the Bessel function is very small, so we can actually approximate this, and the Laplace transform finally can just be approximated by 1. So this means that the non-line of sight interference on the horizontal street is almost negligible, which we don't have to consider it in the later analysis, and also compare the lower bound of the line of sight interference and the non-line of sight vertical street interference, we can see that the non-line of sight vertical interference contributes very little compared to the interference from the line of sight. So the final conclusion here is that the line of sight interference is still the dominant factor in determining the final coverage probability. So in the numerical results, we basically first we feed parameters from our pathloss model to some prior work of the Euclidean pathloss model. The main idea is that we are going to generate a lot of points randomly dropped on the network, and then we're going to calculate a set of the pathloss values based on the Manhattan distance pathloss model. And then we feed these results to two Euclidean models. The first is that the pathloss is simply just calculated by the Euclidean distance of the direct propagation path. And the second Euclidean model is a little bit different from before because it now differentiates the base stations to have line of sight or non-line of sight links, and they assign different pathloss exponents to the different links. And in this case, the pathloss value is determined by if this link is line of sight or non-line of sight. So we are going to denote the Bernoulli random variable with a parameter of the blockage probability in here. And we finally got the results of the parameter fitting by linear regression. And based on these derived parameters, we compared the pathloss models of our model and the Euclidean model, both in coverage probability and ergodic capacity. So our model's result are shown in the blue curves in here, and it is obvious that our model has significant differences from the previous Euclidean distance pathloss model. So this means that the previous framework of the Euclidean model cannot be applied to this new pathloss model in the urban microcells, which moderates our previous analysis of the whole analysis framework in the Manhattan Poisson line process model. So this is the simulation results of the associated CDF of the associated link path gain distribution. So the first observation here, so we in the simulation we mainly consider the comparison of three different cases. The first is that the receiver can only associate it with the line of sight base station. And the second case is that the receiver can either be associated with a line of sight base station or non-line of sight base station on the vertical streets. And last case is that we consider the association to all potential base stations, including those on the horizontal streets. So the first observation here is that our analytical results matches perfectly well with the simulation results. So this verifies that our previous analysis framework is a very accurate characterization of the performance of this network. And another observation here is that there is a very small gap of the CDF with and without the non-line of sight base stations. So you see the CDF here, the gap is only like smaller than 0.01. So this means that the line of sight association still dominates. In most of the cases, the receiver will be associated with the base station on the line of sight street. And then for the coverage probability, we'll compare the coverage probability with simulation results of both considering the line of sight vertical street non-line of sight base stations and consider all of the interference. So we show that this new coverage analysis framework gives very exact and also very concise results. And also we show that the line of sight interference is almost negligible in this network. And for the later analysis, we only need to consider the interference located on the same street as the receiver. So for the conclusion, in this paper, we proposed a tractable and realistic model which combines the MPLP network model and the Manhattan type pathloss model in urban millimeter wave microcells. And the second thing is that the line of sight base stations still dominate the base station association, and also they're the major source of the interference for the typical receiver. And for the future work, we think it might be interesting to have some more realistic street modeling, like considering the street width, or just considering some more realistic data of some major city networks. And also, it will be interesting because this is basically an urban network which considers vehicles, so it will be interesting to consider the vehicle mobility and incorporate this into analysis. And finally, because in this paper we are only considering the performance of one simple typical receiver in the middle, and it will be good if we can incorporate the multiple vehicles inside, and we are going to analyze the total system throughput based on the multiple vehicles. Okay, that's all. Thank you.